Artificial intelligence relies on the ability to find patterns, but it rarely operates with 100% certainty. We need tools to manage this inherent uncertainty. On this board, we have two of our most fundamental tools. First, probability distributions, which essentially act as maps illustrating where our data typically clusters. Second, we have Bayes' theorem, which provides a mathematical framework for updating our conclusions the moment new evidence is presented. Let us first focus on how data clusters by looking at the normal distribution widely known as the bell curve. Consider a manufacturing plant producing water bottles. The stated goal, the target volume, is exactly 1000 milliliters. But in the real world, minor variations occur. When we graph the actual volume of thousands of bottles, they form this shape. The highest point right in the middle represents our mean or average of 1000 milliliters. In a perfectly normal distribution, most of the data points cluster tightly around this center line, perhaps hitting 999 or 1001 milliliters. However, as we move outward to the tails of the curve, finding a bottle with only 950 milliliters is considered one of these rare extremes. To make this intuitive, just imagine throwing darts at a dartboard. Most of your throws naturally cluster right around the bullseye, which represents our mean. As you move further out toward the outer edges, the number of dart holes decreases dramatically. So the core rule to remember here is this. The normal distribution describes systems where most occurrences are average and extreme deviations are infrequent. Now, let us contrast that continuous curve with something much simpler, the Bernoulli distribution. We use this when an event represents a single trial with exactly two possible outcomes. A perfect example is digital advertising. When a user sees an ad, there are only two things that can happen. They might click it, which is a yes outcome represented by a 1, or they might not click, a no outcome represented by a 0. It is completely binary, a single yes or no trial. While probability distributions map out our starting expectations, what do we do when a user's behavior, like wearing an expensive suit, gives us a new clue? To update our probabilities based on fresh evidence, we turn to the math of Bayes' theorem.
Bayes' theorem is essentially the mathematical engine for updating probability based on new information. Let's ground this with a simple scenario. Imagine you're a salesperson in a luxury showroom. A customer walks in wearing an expensive suit. Based entirely on this first impression, you form an initial hunch, maybe guessing there's a 70% chance of making a sale. But then, the customer pulls out their wallet and you see a student ID card. This new evidence completely changes the context. You immediately form an updated hunch with a vastly different probability. This natural way our brains process new clues is captured perfectly by the formula for Bayes' theorem, right here. The formula states that the probability of A given B equals the probability of B given A, multiplied by the probability of A, all divided by the probability of B. Let's break down exactly what each piece means so it's perfectly clear. We always start with our prior probability, which is P of A. Think of this as your original hunch before any new evidence was introduced. Next, we multiply that by the likelihood or P of B given A. This part asks a crucial question. If our initial hunch was actually true, how likely were we to see this specific piece of evidence? We then divide that by the evidence, P of B. This is the total overall probability of this clue showing up under any circumstances at all. When you calculate this out, you get the posterior probability P of A given B. This is your fully updated hunch, the chance of event A happening given that we now know event B has occurred. A fantastic way to visualize this equation in action is as a filter. You start at the top with a large pile of possibilities, representing your original hunch. Then as you pour in new evidence, the math acts like a funnel. It systematically filters out the unlikely scenarios, allowing only the most probable truth to drop out at the bottom. So where is this used in the real world? In the financial sector, it's heavily used for fraud detection. Imagine a bank's AI knows that your normal spending habit is around $50 a day. Suddenly, there is a $5,000 transaction. The AI applies Bayes theorem. It takes the new evidence, for example, the fact that you're currently in a different country, and calculates the exact probability that this transaction is fraud. It also powers everyday tools like email spam filters. If the word lottery appears in an incoming message, the AI updates its belief about the email being spam. It doesn't just stop at one word. It performs continuous updates for every single word in the message until it reaches a high certainty, say 99%, that the message is junk. The core takeaway here is that Bayes' theorem provides a rigorous mathematical framework to continuously refine our beliefs as new evidence emerges. Now let's step into how we can actually code and simulate these probability concepts using Python.
Let's see how all these concepts come together in practice, starting with our water bottle simulation code right here. We are telling the system to generate 1000 random bottle volumes using a normal distribution. We set the target or the mean to exactly 1000 milliliters. When we visualize those 1000 generated bottles, they form this classic bell shape. Most of the individual bottles, represented by these tiny black dots, cluster very tightly around that 1000 milliliter center line. The scale equals 2 in our code controls how spread out the data gets. And if we check the average of all the volumes we just made, it comes out right around our target of 1000, proving the simulation works. Now let's look at how we apply Bayes' theorem to build a spam filter. Instead of code, let's trace the logic right on this probability tree. We start with our prior knowledge. 30% of all our emails are spam, which means the other 70% goes safely to your regular inbox. Next, we look for our evidence, which is the word free. In our historical spam pile, 80% of those junk emails contain that word. But it's not a perfect indicator, because 10% of regular emails also use the word free. To update our belief using Bayes, our code first calculates the total probability of seeing the word free anywhere by combining both those possible pathways. We use that as our denominator in our final Bayes formula to answer the ultimate question: what is the updated chance it is actually spam if we see that word? To really log these concepts in, let's quickly review in our practice and application section. First, remember that in a normal distribution, most of your data points live right here, near the center, the mean. Second, for a Bernoulli distribution, you don't get a continuous curve, you get just two strictly defined outcomes, like a 1 for heads or success and a 0 for tails or failure. And third, the entire heart of Bayes is taking your initial guess, the prior probability, combining it with new evidence you observe, and generating an updated, smarter posterior probability. Let's apply this one last time to our factory sensor problem. Imagine a factory produces a batch of 100 cars. Our baseline probability is that 5 out of 100 are defective, making the rest 95 out of 100 perfectly good. We run them through a sensor test. If a car is actually defective, the sensor is 90% accurate at catching it. But for the perfectly good cars, it still gives a false alarm 10% of the time. If you are standing on the factory floor and the sensor suddenly rings, what is the actual chance the car is defective? You would solve this exactly like the Python logic in the spam filter. Figure out the total chance of the sensor ringing at all and use that to find your updated probability. The ultimate payoff for understanding these statistical distributions and Bayes' theorem is the ability to build AI systems that can reason through uncertainty, mathematically updating their judgment based on new facts just like a human